Hi guys. Okay, so today we're going to look at changing between integral notation and summation notation. So we're going to start with a simple problem, y equals x squared on the closed interval from 2 to 8. We're going to use a right Riemann sum with 3 rectangles, and then we're going to draw the rectangles on the graph. So first thing we need to do is figure out what delta x is. So delta x would be b minus a, which in this case is 8 minus 2, divided by n, which is our 3. So that gives us 6 over 3, which is 2. And notice we're only going from 2 to 8, so we're not using the whole graph. And this base is delta x is 2. This base delta x is 2. And this base delta x is 2. So now I'm going to draw my rectangles. Since I'm doing a right-hand sum from 2 to 4, I'm going to use the 4 to find the height of my rectangle. And I'm going to do the same thing here. Between 4 and 6, I'm using the 6 to find the height of my rectangle. And I'm going to have to make this one longer. From 6 to 8, I'm using the 8 to find the height of my rectangle. And I'll have to make this one longer. And then let's come across and put the tops on our rectangles. And there we go. So now we have our 3 rectangles drawn. So now, what would we multiply together to get the right-hand Riemann sum for this interval of the function? Well, the first rectangle, the base is 2, and then we use the 4, substitute that into the function to find the height. From 4 to 6, our change in x is our base, which is 2, and we substituted the 6 into the function to find the height. From 6 to 8, the base is 2, and we use the value at 8 to find the height of the function. So this will give us 2 times. Now remember, our function is y equals x squared. So 4 squared is 16, plus 2 times 6 squared is 36. 2 times 8 squared is 64. So that's going to give us 32 plus 72 plus 128. That's 232. And there's our sum. Okay, not so bad. Now what we're going to do is we're going to work on writing this nice simple sum in a couple of different ways. So hopefully we can get a general formula for any function. Okay? It's going to look more complicated before it becomes simple. So bear with me. So now the first thing we need to remember is let's consider how we got the 2 in each term. The 2 was the delta x, or the base. That was the base of each rectangle, delta x. And remember, we find delta x by doing b minus a all over n. In this case, how did we get the numbers 16, 36, and 64? Where did these numbers 16, 36, and 64 come from? They came from substituting the right endpoints into the function. They are the heights of each rectangle, right? Now we need a more general way to write our simple sum. We want to be able to apply this method to any function or interval. So this 8 minus 2 over 3, that's delta x. So we have delta x times the 4 squared, right? That's what we've substituted the 4 into the function. Delta x times 6 squared and delta x times 8 squared, right? This is just f of 4 plus f of 6 plus f of 8. So it's the same sum. Now we're going to write it in an even more complicated way, but it's still going to equal our original simple sum. It's just going to look different. So this is still our base, delta x, and it's in every single term, right? But you'll notice it's in there twice. So this was our base. Now our height here is all of this term in each one of these. Now what is making up that height? Now notice what they did. I think you can notice this right here, the 8 minus 2 over 3, that's the base, that's the delta x again, right? And there's another delta x in each of these. But also notice this 2 is in each one of these terms. That 2 is the left endpoint, the starting endpoint of our interval, right? We're on that closed interval from a to b, which in this case is from 2 to 8. Okay, and now there's one more thing that we have in there. We've got a 1, we've got a 2, and we've got a 3. Those are the numbers of the rectangles we're talking about. So this is the first rectangle, This is the base of the second rectangle, and this is the base of the third rectangle. Now, is this the same as the simple sum? Well, we know the first delta x's were the same. So the question is, does this whole height mess equal 4 squared, which is 16, right? Well, delta x, we know in our problem, is 2. 2 times 1 is 2 plus 2 is 4. So since we're still squaring it, we needed to get a 4 so we could square it. In the second one, delta x is 2 times 2 is 4 plus 2 is 6. There it is again. In the third one, delta x is 2 times 3 is 6 plus 2. There's the 8. So it is the same as our simple sum. Now we're going to take this expression and turn it into a general expression that we can use for any function or interval. Okay? So remember, this is our b minus a over n. This is also n, right? This is the first term. This is the exact same thing we had. First term a here, delta x. Now this is counting. 1, 2, and 3. That's counting. And I'm going to show you where that's going to come in a minute. So how does this translate to a general expression? First, remember that the 2 is our a, the 8 is our b. Okay, and instead of 3 rectangles, we're going to use n rectangles. So here we go. We know that delta x is b minus a over n. That's a rule we already know. Now the height of each rectangle can be represented as f of a plus delta x times k. Remember, if we look back at this term right in here is f of the 2 was a plus this was delta x, and this is the k, which counts which rectangle we are in. Okay? So that's the function value that we're going to use. That's going to be our height. Okay? And we already know that the base is delta x, which is b minus a over n. So if we want to find the area of the rectangle, we do the base delta x times the height of the rectangle, which is that function value evaluated at a plus delta x times k. Now that's the area of one rectangle. We have to add up all the rectangles. So if we look at this, if we want to add up all the rectangles, we use a summation as k goes from 1. Now k is the variable that's going to count how many rectangles we have. The first rectangle, the second rectangle, k will be 1, then k will be 2, then k will be 3, all the way till it gets to n. And this was our base, and this is our height that we're multiplying. And we're going to do it for each k value until we get to n, and we're going to add them all up. But we also need an infinite number of rectangles. So that means we're going to make our number of rectangles approach infinity. That's a limit. That's where this limit as n approaches infinity comes from. Okay? So far so good? You still with me? So let's stop for a minute and just recap the procedure to write in summation form. First thing you're going to do is you're going to find the width of each rectangle in the interval from a to b. That means find delta x, b minus a over n. The next thing is we're going to find the right end point of each rectangle. We're finding the x value that we're plugging in. We're finding the first term plus delta x times k. Next thing is you're going to find the area, which means you're going to do delta x times, and you're going to plug that x of k into f. And this one, delta x times f of a plus delta xk, might be the easier one to use. Now, we've been doing a right Riemann sum, okay, a right one. So the right Riemann sum starts at k equals 1. Now, sometimes they'll change the k's to i's. It doesn't really matter. So it's the summation as k goes from 1 to n, because we use, when we're doing a right Riemann sum, we don't start at the first position 0. We use the right side of the first rectangle, which would be at 1, all the way till the end of the interval, which is at n. And we do the height times the delta x. So that's the summation as k goes from 1 to n of f of a plus delta x times k times delta x. Now, if we want a left Riemann sum, it changes a little bit. because when we use a left Riemann sum, we start at the leftmost endpoint, so we let k be 0 before we have a rectangle, and we only go to n minus 1 because we're not using that rightmost endpoint in our function to find the height. So then we use that same f of a plus delta x times k of delta x. We just have different limits on the summation. And there is the midpoint Riemann sum. We're back to k going from 1 to n, but now we use f of a plus delta x times 2k minus 1. That's going to find the midpoint of each interval for us, okay? That'll find the midpoint of each interval, and we multiply by delta x. So this is what we have. Now let's see if we can actually apply this to a problem. So let's use the procedure above to write the expression that represents the approximation shown below, given that f of x equals 2 over x plus 3. Now, for the first few problems, I'm giving you this template here of things to look for to help walk you through the problem. So the first thing is I'm going to write down 2 over x plus 3. That's my f of x. Now I'm going to look at the picture. My graph here, my rectangles go from 1 to 4. Those are my a's and b's. So a is 1 and b is 4. I'm also going to count here. There's 1, 2, 3, 4, 5, 6. There are 6 rectangles. So let's find delta x. Now remember, delta x is b minus a over n. So that would be 4 minus 1 over n is 6. That's 3 over 6, which reduces to 1/2. Now, we're going to find a plus delta x of k. My a is 1 plus my delta x is 1/2 and times k. So I could just make that k over 2, or you could use 1/2 times k. Doesn't matter, but make sure you have that 1 plus. Now, we're going to find f of this. So we're going to take this a plus delta x times k, and we're going to substitute that into f of x every place there was an x. So our f of x is 2 over, now instead of x, we're going to write 1 plus k over 2. Then the rest of the function was plus 3. Now we're ready to write our limit. So this is going to be the limit as n heads to infinity of the summation as k goes from 1 to n of, now our f of a plus delta x times k is 2 over 1 plus k over 2 plus 3 times our delta x is 1/2. And now we have our limit. Now, just a reminder of a few things, okay? A definite integral represents the area under a curve of a function, and a Riemann sum gives us an approximation of that area. Remember that if we want an infinite number of partitions or rectangles in that Riemann sum, the approximation gets closer and closer to the actual area of the subintervals of the Riemann sum. Right? We talked about this, and we can't take Riemann sums with infinite rectangles because n equals infinity, and in our summation, because infinity is not a number. You cannot substitute it in. However, if we have this right Riemann sum, we know, remember, we've already learned that the area is the integral from a to b of f of x dx. And now we know that's the same as the limit as n heads to infinity of the summation as k goes from 1 to n of x sub k times delta x, or if you prefer this one. And not only that, I know it's also equal to the limit as n approaches infinity of the summation as k goes from 0 to n minus 1 of f of a plus delta x times k times delta x, right? That's if I use my LRAM. And I know that it's equal to the limit as n approaches infinity, the summation of, as k goes from 1 to n, of f of a plus delta x times 2k minus 1 times delta x. That's if I used my MRAM. They are all the same thing. So the definition of a definite integral is if you have a continuous function f of x over the closed interval from a to b, we know that that's the definite integral from a to b of f of x dx. That is the area of the function under the curve, between the x-axis and the curve. We have the definite integral, and it's also equal to all of the limits of each of those Riemann sums, no matter which way we do it. Okay, what we saw on the other side. Now remember, this wrote it that way with the x sub k, but remember the x sub k is this. You're going to see it written both ways, so I want you familiar. And remember, your delta x is b minus a over n. Now at the bottom of the page, I've put a graphic here for you, just to give you a reminder and another problem that's all worked out, okay? And to show you how that equals the definite integral. When you look at the problem here, the width of the base is at the end here. This is our delta x. Now, this is our entire function. That's the height of the rectangle, the function. But this piece in here, that's the value of x. That's the x sub k. This piece is your a, and this piece is your delta x times k, or in this case, times I. Notice the delta x was 6 over n, and then they multiplied by I instead of k. It doesn't matter if it's an I or a k. Notice your summation. I is going from 1 to n. Now, if what's in the parentheses is all our x, then our function is 2 times x plus 5. And that's where this function comes from. And then you see it here in the integral. Okay? Now, we also knew that a was 2. We also know that delta x is 6 over n, so that's equal to b minus a over n, which lets us find b equals 4, and now we're able to write it as a definite integral. Let's try one. Okay, so we're going to be given this graph. F of x is 1/2 x squared plus 1 on the closed interval from 0 to 4. We're going to find the exact area can be expressed using the definite integral. So we have the definite integral from 0 to 4. That means my a is 0 and my b is 4. Of 1/2 x squared plus 1, that's my function, dx. Now that dx is just like our delta x. The dx is the change in the x's, just like the delta x is the change in the x's. Now we're going to have to figure out the delta x in a minute. Okay, it also wants us to write the definite integral as a right Riemann sum with 8 equal subdivisions. That 8 is our n. So now we can find delta x, which is b minus a over n. The b is 4, the a is 0, and the n is 8. That gives us 4 over 8, which is just 1/2. Next up, we can write our x value. Remember, this is x sub k. We take the a, which is 0, plus delta x is 1/2, and we're going to use I instead of k this time. Now, please, do not tell me 0 plus I over 2. What is 0 plus I over 2? It is I over 2. Now, we're going to take this value, and we're going to plug it, because that's this, and we're going to substitute it into f. Now, f is the function 1/2 x squared plus 1. So every place there's an x, we're going to put this I over 2. So our function is 1/2 something squared plus 1. And the something is our I over 2. Now we're ready to write our limit. So this is the limit as n heads to infinity of the summation as I goes from 1 to n of, now our function value, that's the 1/2 times I over 2 squared plus 1 times our delta x is 1/2. And there we go. Good. Now let's go the other way. Now I've given you the limit and I want you to write the integral for me. Then we'll use our graphing calculator to check that both forms give the same result. Okay, so let's take a look at what we have here. This is going to be my delta x. So my delta x is 5 over n. I'm going to write that in here. Now notice I have 5 over n times k. That's my delta x times k. And they put the plus a at the end. So this minus 2 is my a, negative 2. So let's take a moment delta x equals b minus a over n. Delta x is 5 over n. So we need b minus, our a is a negative 2, so that's plus 2 over n. That means that 5 has to equal b plus 2, so b must be 3. Now, what is the a plus delta xk? That's this part in here that's in that parentheses, right? The negative 2 plus 5k over n, and we had minus 2. Now, if that's the x value, that's the x sub k, so we're going to call that x. Now we're going to read the function 5x minus 1. That's our function. So now we're ready to write our definite integral. So it's the integral from a to b. So the integral from negative 2 to 3 of our function is 5x minus 1 times dx, right? That delta x becomes the dx. Now we're going to go to our calculator and make sure they both give us the same value. So here we are on a calculator page, and we want to evaluate the limit as n heads to infinity. Now notice, we can't take a limit on our calculators. That only works on the CAS calculators, so we don't have that ability. So what we need to do is let n be a very large number in our summation. The problem is we have to pick a number that's large enough, but not too big that the calculator gets stuck calculating for too long. So let's do the summation as k goes from 1. Let's try 1,000. I think that should be pretty big. So 1,000. Now that means that every place we have an n, we're going to put 1,000. Okay, so we had the summation of 5 times, and we need the fraction template, 5k over, now instead of n, we're going to put that 1,000 again. 1, 2, 3. Then I'm going to arrow out of that, subtract 2, close that parentheses. Then don't forget to subtract 1. Then we're going to close another parentheses, and we're going to multiply by the fraction 5 over. Now instead of n, we're putting 1,000. We'll press enter, and that's the sum we got, which is a fraction. So I'm going to hit Control Enter so that we have it as a decimal, so we can see how it compares to our integral. So now we're going to go back to the template key. We're going to get our integral, and we said that this was the integral from negative 2 tab to 3 tab. Our function was 5x minus 1 tab over dx, and we press enter, and it's 7.5. Now notice our sum was 7.5625, but that's because we picked an arbitrary 1,000. If we actually let n head to infinity and took that limit, they would be equal. Now, just something I want to point out here is that sometimes a Riemann sum in simplified form needs to be unsimplified before being able to translate it to an integral. For instance, if you look at this, k cubed over n to the 4th, I don't see my delta x, but I have this k cubed and n to the 4th. I could factor out a 1 over n. That is my delta x. That leaves me with a k cubed over n cubed, or k over n cubed. That's going to be my delta x, that's the 1 over n, times k. And my a is 0, so the a plus delta xk. Notice also, this is all my x value. So this is my x cubed. That's where my function x cubed comes from. And since my a is 0, my lower limit is 0, and 1 over n is my delta x. That has to equal b minus a over n. So 1 has to equal b minus a is 0, b is 1. That's where the upper limit comes from. So let's try one that has to be simplified. Now this one, we need to come up with a general rule. for this sum. We have the limit is n heads to positive infinity of 1 over n cubed plus 4 over n cubed plus 9 over n cubed plus dot 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 plus n squared over n cubed. So first thing we need to do is find our delta x. So we're going to factor out that 1 over n, because that'll give us an n squared over n squared, which is a nice number 1 to end with. Now if we factor out the 1 over n, that leaves us with 1 over n squared plus 4 over n squared plus 9 over n squared, all the way to that plus n squared over n squared. So if we try to write this as the limit as n heads to infinity of a summation as k goes from 1 to n, we need a general rule here. So think about your k's. First we have 1, the first rectangle, the second, the third, all the way down to the nth. What's happening? In the numerator of each, we're squaring that k, right? 1 squared, 2 squared, 3 squared, n squared. And the bottom is always n squared. So that means we have k over n being squared times our delta x, 1 over n is still hanging out there. So now we have a simplified version. Our delta x is 1 over n. Okay, our a plus delta x times k is just k over n, which means we really added 0 for a. We now can find our b minus a over n is delta x. So 1 over n has to equal b minus 0 over n. So b must be 1. Now what function did we substitute this k over n into? K over n is being squared, so f of x is x squared. That means our integral is the integral from a to b is 0 to 1. Our function is x squared, and then this delta x becomes dx. Now we're going to go to our calculator and make sure that the summation came out to the same answer as the integral. Okay, so this time we're going to do the limit. Again, we can't do the limit as n heads to infinity, but let's do that summation again, and we'll use that same trick that we're going to use the summation as k tab goes from 1 tab, and we'll go to 1,000 again. 1, 2, 3, and tab over. And our rule was open parentheses. We need a fraction. We have k on top, n on the bottom. Arrow out of the fraction, close it, square it, times, open a fraction, and our delta x was 1 over, and I messed up because I put an n. We're going to change that n to a 1,000. So I'm going to come back here, delete this, change that to a 1,000. I'm so used to my n's, but we had to let n be a really big number, and we've got another fraction. So again, I'm going to hit Control Enter. So we have 0.3338335. Now let's see what our integral gives us. We use the template key. We get our definite integral there, which goes from 0 tab to 1 tab. We have x squared tab dx. Hit enter, we get 0.3 repeating. So those are pretty darn close considering we only guessed at 1,000. We did not let n go to infinity. Okay, we're going to try one more. We're going to translate this Riemann sum into a definite integral. Then we're going to use our graphing calculator to check. Now, if we look at this limit, we have the limit as n heads to infinity of the summation as k goes from 1 to n of the natural log of 1 plus 16k over n times 8 over n. That 8 over n is our delta x. But this is not delta x times k. So we need to manipulate this a little bit. So I'm going to bring down here the natural log of, and I'm going to leave some space because I don't know what I'm going to do. I know if I have 16k over n, I need to factor out a 2, right? If I factor out a 2, that'll give me 8k plus n. But the problem is, if I distribute that 2 through, I'll have 2 plus 16k over n, which means I also needed, that means I added an extra 1, so I also have to subtract 1 off it. So if I do this, now I should have the same thing, right? Because 2 minus 1 is 1 plus 16k over n. Now I have the same function. So we're going to look at this as the limit as n approaches infinity of the summation as k goes from 1 to n of the natural log of 2 times 1 plus 8k over n minus 1 times our delta x is 8 over n. So here we go. This is our delta x. I'm going to write that in there. Delta x is 8 over n. This is our a plus delta xk, which means that our a is 1. And that also means delta x equals b minus a over n. We know our delta x is 8 over n. That has to equal b minus our a is 1 over n. So 8 has to equal b minus 1, and b is 9. So what is our f of x? What did we substitute this into? We have the natural log. Remember, this is our x of k. So we have the natural log of 2 times x minus 1. So f of x is the natural log of 2 times x minus 1. Now we're ready for our integral. It's the integral from a to b, so the integral from 1 to 9 of our function is the natural log of 2x minus 1, and the delta x becomes our dx. Okay, now we're going to go to the calculator and see that we get the same value for the limit as we do for the integral. So here we are again. We need to do a limit as n heads to infinity of a summation. So again, we're going to take a summation. We're going to let k tab, and it's going to start at 1 tab. Now we can't let n go to infinity, so we're going to pick a large number for n. Let's try 1,000 again. It seems to be working for us. We're going to tab in there. We're going to control e to the x to get our natural log of 1 plus, now we need our fraction template. We need a 16k over n, which is 1,000, because we substituted a value in. Get out of that, close the parentheses, open new one, control fraction for our delta x is 8 over, our n is 1,000 that we're using for a big value. We press enter. We get about 16.093636. Let's check our definite integral. So we use our template key again. Here's our definite integral, which we said went from 1 tab to 9 tab. Our function was control to get the natural log of 2x minus 1 tab and make that dx. Hit enter, and there we go, 16.0823. Those are pretty darn close considering we're just picking a fairly large number and not letting n go to infinity. Okay, guys, we are going to stop here. We've done a lot of work on converting between summation notation and integral notation. I know it's tricky. We're going to keep working on it, okay? One step at a time. Have a great day, guys. Bye.